Today we'll be doing proofs about line segments and also introducing yourself to wonders. Horrible proofs. Proofs are not fun. Or maybe. It depends on the other up. But let's jump right in. So in front of me I have a list of all the properties you'll need to know for proving line segments. And most other too. Line segments and angles are going to be mostly the same thing. For angles, the only difference between angles, there are some differences. Like, for example, when you're talking about angles, instead of saying segment addition postulate, you say angle addition postulate. But we'll go to more depth in that when we get to angles proofs. So let's go through all of these theorems, proofs, whatever. So the first one you should already know, the segment addition postulate. Given a diagram like this, here, AB, sorry, I don't know why I do like that. Segment AB plus segment BC equals AC. That postulate isn't proven, but is assumed true. You cannot prove a postulate. And then the next one is the definition of congruent segments. So if you have two segments that are congruent to each other, then it also means their measures are equal. So that's pretty straightforward. Now we have the commutative property of addition or multiplication. So for multiplication, if A times B equals B times A. In addition, A plus B equals B plus A. This is useful for substitution and other stuff similar to that. Now the symmetric property states if A equals B, then B equals A. Straightforward. Again, this is different from the transitive property, which is next. Transitive property, if A equals B and B equals C, then we can say A equals C. See how we took multiple different equations and set them equal to each other? That makes sense. So we have, like, let's say 4 and 12 are variables. 12 equals 16, then we can say 4 equals 16. And this can go on for as many times as you want. You can say 4 equals 12, 12 equals 16, 16 equals 24, 24 equals I, for saying. And now we know 4 equals I. Substitution property equality is different from transitive. Something to note, in proofs you can always use substitution property in place of transitive, but you can't always use a transitive property in place of substitution. So when you're doing substitution, we have A equals B. Now we're plugging B directly into an equation. So here is B, and we're plugging it into here, for example. No, actually, that's wrong. Plugging this into here. Now that's where we get B plus B equals C. So you can't really use transitive there because B is not equal to anything. That's the sum of A plus B. And now we have the properties of multiplication, addition, subtraction. These are the properties you use when you're proving the algebraic proofs. Yes. Now we have the transitive property of congruence. So this is similar to the transitive property, but talking about congruence. A is congruent to B, B is congruent to C. That means A is congruent to C. That's really depressing. So that's really, really, really straightforward. Now we have the symmetric property of congruent. A is congruent to B, B is congruent to C. Cool. But now we have the reflexive property of Now you may be asking yourself, when exactly is this useful? So let's say we know A equals 12 and A equals X. And we want to get to the point where we can say X equals 12. Now, one of the ways you can do this is you could substitute X into here. But sometimes another way you can do it is also by saying A equals A. And when we say A equals A, now we know what the two values of A, so we can plug them into each other, and that goes 12 equals X. And sometimes your teacher may also make you write reflexive property, but you have to ask your teacher that. We have the reflexive property of congruence, basically the same thing. Something to note, when you're talking about congruency, there is no substitution for congruency. Now we have the definition of the midpoint. A midpoint divides a line segment into two congruent segments. When I say two congruent, I mean that. You cannot say for the definition of midpoint, a midpoint divides the segment into two equal segments. They're congruent. So here's an example. Just a diagram, it's obviously true that M is the midpoint because of the congruency markings. And we could assume that M is congruent to MB, and that's because of the definition of a midpoint. And over here, segment markings. Now it's time to get on to our first proof. Given M is a midpoint of AZ. So kind of like what you did with algebraic proofs, you're always going to write the given as your first step. depending on what, well, almost always. There's some cases where you don't. So now the diagram is a part of the given if you're curious. So now let's go in and see about how we can get started on this proof. So we know M is a midpoint. So now we can now we already know 2x plus 14 minus 1. But before you solve it, remember, we have to prove it down here in this statement and reason chart. So you can honestly make a concession. You can honestly not prove it first and figure out how you would prove it out normally. So you would prove it like this. Minus 14 minus 14. 2x equals 5x minus 15 minus 5x. 3x equals negative 15. X equals 5. So you did that. Now what you're doing is translating all of these steps. All of these steps you just did into here. But you also have some additions. So the first step is always given. So M is the midpoint of AC. So now we're getting started into like actual proof. Your 2-column proof. So that's given. That's pretty obvious. But before we go on, now we got to basically say, what does it being the midpoint even mean? So because M is the midpoint, we conclude segment AM is congruent to segment MZ. That is because of the definition of a midpoint. That is what a midpoint means. So now that we have that, what are we trying to prove again? So we're trying to prove x equals 5. And to do that, we got to figure out how to set these two equal to each other. So, and we know the values of the segments. So all we got to do is just set the segments equal to each other. So now we got to turn this, say, AM equals MZ. We cannot remember, AM cannot be congruent to something like x squared. That is not possible. That's what its measure equal. When you're saying congruence, you're talking about type of shape equals. So now we're going to say AM equals MZ. That is because of the definition of congruent segments. In the definition of congruent segments, sometimes you'll also be allowed to write, instead of the title, which is like which the title is basically definition of congruent, angle addition postulate, something like that. You can also write what it means in some cases. So if I didn't remember the definition of congruent segments off the top of my heart, I could write like, if segments are congruent, then their measures are equal. And look at that. It's an if statement. It's a conditional like you did earlier. If hypotheses, then conclusion. And any theorem, by the way, is true. So, like, example, let's think about, well, definition is true. I'm sorry. So let's think about the definition of a right angle. A right angle is a 90-degree angle. So we can say if an angle is right, it's 90 degrees. If an angle is a right angle, it is 90 degrees. So that's what our definition is basically saying. But now we can check if the converse is true. For a definition, the inverse and the conditional and the inverse is true. Conditional, whatever. So now we can say if an angle is 90 degrees, then it is a right angle. That is also true. So now we know we can write a biconditional saying an angle is a right angle if and only if it is 90 degrees. And that's basically what our definition is saying. We'll want to probably have it in if then form. That's like easy to understand. So now let's go on to our next step. M equals MZ. So now what do we know about AM? What do we know about MZ? We could go back to the diagram. Hold on, I was like very poorly wrote. So we know AM equals 2x plus 14. Let's scribble that down. And we can't write both of these in the same step, by the way. We can't write what AM and MZ equals in the same step. So now we're saying this is given. because it's in the diagram. And we can say, like, diagram as shown. Or something like similar to that. Of course, you might not have to do it, but you might want to write it just to make it easier to understand where it's coming from. And you basically, when you're doing a proof, you basically assume whoever is following along with the proof doesn't understand anything. Now, the same thing for MZ. MZ equals 5x minus 1. We cannot say MZ also equals 2x plus 14 because we would first have to show. We know they're congruent, then we would have to plug it into each other, and that would be a little different. And also, we're not trying to say that. Quick thing. When you have the next step in a proof, and that reason is the same as a reason on top of it, so in this case, these reasons are the same, you can use quotation marks to represent they're the same. Your teacher might not allow it. Usually, you'll probably be allowed to. But it's always good to clarify. Not everything I was taught is your teacher agree on it. It's what it allows you to do. We need more room already. Okay, whatever. Now we know AM equals MZ. So now what we're trying to do, so I told you we're trying to set the two equations equal to each other. So basically, we're plugging this into here, or plugging this into here. What is that? The substitution property of equality. Or technically transitive too. 2x plus 14 equals. Oh yeah, by the way, when you're running your own statement and reason chart, you may be asked the numbers, so be clear about that. So now we substitute it in. So our reason is going to be our substitution property of equality. And to make this understandable, well, you're basically substituting from this step, substituting from these two steps. Sorry, I can't get the right color. Substituting from these two steps into here. So that's exactly what you're substituting. And now we're basically doing it like a normal algebraic proof. 2x, sorry, x minus 5x. Wow, I'm so laggy. 5x minus 5x minus 1. Now at this point, I usually just like to stop writing the reasons. Or I usually write the statements first. But that's like besides the point. This was subtraction, POE. Dude, I'm so laggy. I don't know why it's so laggy. That's really weird. -3x equals -15. This is actually my crush. This is the same, so we can use the quotes. Oh, I made a mistake here. So sorry. Let me write this out. This is simplifying because we're simplifying it. This is. Now I'm cutting it out. And now we've proved it. X equals 5, and this is simplified. So that's officially your first two segment proof. Geometric proof. So now we're gonna go on to the next one. I'm also gonna do that. I think that one like laggy here. There we go. So let me find another proof, which is gonna be good to understand. So we're not gonna add numbers. So if we go through, oh here, this is perfect actually. So this actually uses a lot of stuff. Sorry, wait. Given AC equals AB plus AB, I have a little chart. So now let's jump right into our proof. So what is the first thing we know about this? Sorry, let me write out a statement. So wait, what are we actually trying to prove? trying to prove B is the midpoint of AC. And now we can go back to what the definition of midpoint means. A midpoint divides a line segment into two congruent measures. So effectively, what we're trying to say is the only way we can say B is the midpoint of AC, AB has to be congruent to BC. So that's effectively what we're trying to prove. That will allow us to use the definition of the midpoint. So now let's jump right into the proof. Also, something to know about geometry is so much different than like factoring a quadratic. When you factor a quadratic, you're given a specific way you gotta do it, and that's gonna be the way for everything. But geometry, like proofs, you're not given a specific way. There are multiple different ways to solve the same thing. Something you may have questions you've never seen, but you gotta use thinking. It's just sad. So let's jump right in. So AB, AC. So this is step 1. I'll start numbering steps actually. And first reason given, yay, 2. So now what we want to do, sorry, I'm losing it right now. Remember, we're trying to prove B is the midpoint of AC. So we gotta really show how B equals BC. And if you need something like this, something I like to always do is try using the segment addition postulate when you're dealing with segments. It's a really nice way, and a lot of times it works. Of course, there are cases where you don't, but sometimes it will work, sometimes it won't. Not all proofs require it. So now our next step's going to be segment addition postulate. AB plus BC. Remember, alright, good. Now step 3. Okay, hold on. Now that we have two things equal to AC, what we could do is substitute them into each other. So you could use transitive or substitution. Wow, I miscircled that. So we're setting AC equals AC, and we can write it like, first of all, if you have to use reflexive property, I'm going to use reflexive property so you get a better understanding. AC equals AC. It might be easier to follow along too. This is a reflexive property of equality. Now we're plugging it into each other. AB plus AB equals AB plus BC. This is our substitution. PLE. Now we're going to try isolate. So now when we simplify this together, it's okay. So AB plus AB. See, we have a common side of AB. So we could get rid of this. We could get rid of the AB on both sides. Good. And this is step 5, which is the subtraction property of equality. Now, once we cancel out these terms, all that's left is AB equals BC. But we're not done yet. Remember what the definition of midpoint is. Divides into two congruent segments. You have to write proofs as they are. You cannot say they have equal measures until you prove that in the next step. So this is step 6, so to simplify. Now we can change this to AB is congruent to BC. And what is that for? The definition congruent segments. If two segments are congruent, then their measure equals. And the same thing for the converse. If two segments have equal measures, then they're congruent. Now we said this, and we don't have to write any more steps. Now we can say B is the midpoint. Sorry, that was like messed up. Midpoint. That's misspelling. Midpoint of segment AC, RP. That's really bad handwriting. And look at that. Wait, did I remember my steps? 2, 3. Oh yeah, I use reflexive property. I forgot. Now, this is the definition of a midpoint. See how, if you're confused on why we can just write definition of midpoint now, well, let's look at the diagram. We know AB is congruent to BC now that we've effectually proved that. When we have a midpoint dividing a segment with like 3 points, then these smaller segments are congruent. And if those are congruent, that tells you, because what a midpoint does, that tells you B has to be the midpoint. So that's why we can say B is the midpoint of AC. So those are your first 2 line segment proofs. Hope you understand. If you have any questions, comment it below. And that shall be it. Good luck. Next time is angles.